Hello there, cutie patootie, math angel. Welcome back, welcome back, welcome back. And a very warm welcome to you. If you are new around here, this is Decaf-Math, ASMR. And today we are going to do a little bit of geometry review. I've been getting several requests to continue on in geometry, so this is just a random topic. Eeny, meeny, miny, mo. Eeny, meeny, miny, mo. So today we are going to be talking about some postulates that have to do with triangle congruence. So we'll define those, we'll review what a triangle is, and then we'll talk about what congruence means in this context, which is funny timing because I think my last video was about congruence as well, but in the context of modulo, so unrelated. But we're going to go over what congruence means here, and then we're going to talk about those postulates, okay? So we'll just take our time, no rush, no rush, no rush. So, as always, I wanted to remind you that there's absolutely no comparison here. It does not matter whether you like math or hate math or unsure about how you feel about math or just somewhere in between. It does not matter whether you think that you're awesome at math or you think that you're terrible at math or also somewhere in between. We're just here together right here and right now. And if you're watching this, I for one very much appreciate you, and I appreciate the chance to share this moment with you. So let's enjoy this. I will say I think that this is both interesting and also kind of boring, if there's such a thing. I know that we're gonna have a relaxing and enjoyable time. I will anyway. Okay, so are you ready? Are you ready? You can take notes, study along, you can zone in and out, you can close your eyes and start to fall asleep. You can bring your own little hobby as well. Anything goes, anything goes. Alright, so let's first review what a triangle is and what congruence means before we talk about the postulates that justify this congruence. Let me grab a pencil. Oh, do you want one? Yeah, of course. Of course you can borrow one. Let's see, I'm gonna take this one, and you can have, here, you want a mechanical one? Yeah. There's lead in this. I thought there was. I'll deal with that later. Let's see, how about, well, I guess I only have one mechanical one, but you take this one, and this one definitely has lead, and I'll take this one. Okay, so I'll leave that for you. And, okay, so what is a triangle? A triangle is this is a triangle, this is a triangle, this is a triangle. It's a shape that has 3 sides. 1, 2, 3. It has 3 vertices, which are these end points here, A, B, C. And it also has 3 interior angles. Doop doop here, doop doop here, and doop doop, forming this angle. So we have 3 sides, 3 vertices, and 3 interior angles. Okay, so triangle. So we can have all kinds of types of triangles, different lengths of sides, different angles here. Here, there's a cute little baby triangle. And bigger triangles, and they can be oriented all kinds of ways, right? Doop, doop, doop. But we're gonna stick with these this way for today, okay? Okay, so congruent triangles are when we have 2 triangles that are exactly the same. So basically, if I start with this triangle, let's say A, B, C, and I cut it out, keeping the angles and keeping the lengths of the sides, and I cut it, and then I just paste it somewhere without stretching it, without doing anything weird with the angles, just taking it and placing it. So I can flip it, I can rotate it, and that's fine, and then I can shift it and move it around. But as long as that actual triangle stays the same exact way, I have a congruent triangle. Okay, so that would require, in theory, that the lengths of all 3 of those sides are the same, like corresponding lengths anyway. Okay, also the interior angles that are corresponding to each other would also be the same, so they come in pairs. This and this, this and this. Now I'm kind of hesitant to say that this bottom left one matches this bottom left one, and this bottom or this top one matches this top one, and this bottom right matches bottom right. That's not always the case, because if this were, let's say, rotated or flipped, then they don't always line up that way. We'd have to actually measure it, or we'd have to use some logic to find which angles actually correspond to each other. Okay. In this case, though, we'll come to see that these 2 do correspond, and these 2 correspond, and these 2 correspond. So when we talk about sides being congruent, that means that the lengths of the sides are the same. If we talk about angles being congruent, then that means that the measures of those angles are the same in degrees or radians or whatever unit, but their measures are the same using our protractor, right? And if we talk about triangles being congruent, that means they are the same triangle, meaning they have corresponding sides that are the same length or are congruent, and 3 corresponding angles that are congruent. So we should have 3 pairs of angles that are the same measure in some way, and 3 lengths of sides that are the same in some way. Okay, so that's what congruence means. So that's 6 different things that need to match up. Now, what the postulates do is that they give us a way to not have to show all 6 things. It's like a little shortcut. So instead of having to show that the three sides have corresponding congruent sides from one triangle to the other, and three angles being congruent in some way, we can instead have just 3 of those 6 common pairs in such a way that we can conclude that the triangles are congruent without having to show the other 3. So let me show you what I mean by that. So let's start with this first pair here that I've drawn out. Okay. So these 2 triangles, and we usually label triangles or name them by their 3 vertices. So A, B, C, and X, Y, Z. This notation says that this side here, AB or BA, the order doesn't matter there, the length of this thing is the same as the length of XY or YX, because this one dash matches up with this. So it's like if I'm given this diagram, this is what this tells me. ABAC, XYZ are triangles. AB has the same length as XY, and the two match here. So BC has the same length as YZ. That's what this notation is. And this AC length has the same length as XZ. Now the reason that it's 1 and 1 and then 2 and 2 and 3 and 3 is to differentiate the actual measures themselves. So typically if I have 1 and then 2 like this, that usually means that the length of AB is not the same as BC. So even though it kind of looks like this could be an isosceles triangle or even an equilateral for that matter, by this actual diagram, these 2 are not necessarily the same length. So usually if I'm trying to show that 2 of the sides are the same here, even though this is the same length as this, if I also want to show that BC is the same length as AB, I would just have the one dash to show that this is the same as this, which is the same as that. So it depends on the kind of information that I want to show or represent in my picture. So in this case, this part is not necessarily the same length as this, and some teachers prefer to even assume that that's not the same, unless somehow your question gives more information, So the key information here is that this side is congruent to this side. They have the same lengths. This side is congruent to this side. They have the same lengths. And this side are congruent and they have the same lengths. So that's what we're trying to get out of this picture here. Okay? So what does that mean? It means we have 3 sides and 3 pairs that are congruent. And according to what we call the SSS postulate, side, side, side postulate. I know, so original. Postulate. We would then conclude that triangle ABC is congruent to triangle XYZ, or Z if you're cute. But we would write triangle ABC like that is congruent to triangle XYZ. And the order here does matter, so in a way. So the important thing is that the vertices correspond to each other. So if I start with A and then go up to B and then go to C, then I would start with X and then go up to Y and then go to Z. But you could do like C, A, B, and Z, X, Y, okay? Or, any other combination. But you go this side, this side, this side. Then for this, you'd have to go this side, this side, this side, okay? So S is side. And then for the other ones, A is going to be angle. We'll talk about that in a Do you see that? So basically, in short, if we have two triangles and we know that corresponding sides, and we know all three are congruent, then we can call on the SSS postulate to tell us that the triangles themselves are congruent without having to show that these corresponding angles are also congruent. To prove it, I think the easiest way would be to throw in some trigonometry, but we don't need to do that for geometry. So that's it. So that means that we don't have to actually show these angles. We can just conclude that the triangles are congruent. Now the cool thing is, now that we've called on SSS to show that these are congruent, then once we already know they're the same, then we can actually use that fact to then justify that the corresponding angles are congruent. So corresponding parts of congruent triangles are congruent. The parts being the angles or the sides. Okay? Okay, so let's just compare that with this next one, and I think we'll start to see this pattern here. Alright, so let's say we have these two triangles now, PQR and LMN. And so, again, for now, I'm not going to worry about rotating stuff. Okay, I'm not going to worry about flipping or rotating for now. We're going to do more complicated type of questions. But I want to make sure that we understand the postulates first. So, in this diagram, okay, let's just look at the picture. We have two triangles, right? And so this tells me that the length of PQ is the same as the length of LM. This just says so. And then I have the length of QR is the same length as MN. So this doop 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 doop. Okay? And we have this angle that we call PQR is the same measure as LMN. That's an angle here. So if we're just given a side and a side, and then an angle and an angle, and another side and another side, without knowing anything about this third side or these other two angles, I can actually just go ahead and call on the SAS side angle side postulate to conclude that triangle PQR is congruent to triangle LMN. Okay, so I'm calling on SAS postulate, side, angle, side. Now, the order here kind of matters in that we need to start with the pair of sides that are congruent. The angle comes next. So this angle is going to be the angle between the two sides. So if my diagram had a random angle like here, that would be a different thing, okay? So SAS specifically is, like, it doesn't matter which pair exactly, so I could just say these two these two sides, and then this angle, that's fine too. But it has to be a little sandwich. Side, angle, side. Side, angle, side. Okay? So SSS, SAS. Okay? So again, what's the point of this? Well, we have three corresponding pairs that are congruent. So we don't have to show that these two are congruent and then these angles are congruent, because like we said, if they are truly congruent, all six pairs will be congruent. So the lengths of the sides and corresponding lengths of sides and corresponding measures of angles. But in this case, we have a little shortcut. If we show that we have two sides and then an angle and then two sides, then then we can conclude that it's congruent, and therefore conclude that all the other pairs that we didn't do are also congruent. Okay, so that one's allowed. So you can probably guess where we're going with this now. So now we have, let's see here, oops. Now we have, let's see, triangle DEF and GHI. I know I'm very original with these letters, but here we have two angles, corresponding angles that are congruent. That's what this tells me, at least with this notation. Then this side here, these two are congruent, so the same lengths, and this angle is congruent to this angle. So what do we have here? We have an angle, and then a side, and then an angle. So ASA, okay, like that. ASA postulate, angle, side, angle. And so if I'm given two triangles with this kind of information in some way or another, or, we might have to do a little bit of work to get to this, but then we could conclude without having to figure out that these two are the same and then these other pairs are all the same. We could conclude that triangle DEF is congruent to triangle GHI. Okay, so again, as long as the vertices are corresponding to each other in a way that when I label out the angles and the sides, that they would be corresponding, then that's how we'll want to name the triangles here, like to represent that they're congruent, okay? So in this case, they are oriented this way without flipping or anything, okay? Alright, so ASA is one, so SSS, SAS, ASA, and then there's only one more, and that would be this little one, this little guy. We have alpha, beta, gamma, and JKL. So we see that we have two angles corresponding that are the same measure. Angles here, so angle, angle, and then the length of a side. So AAS, angle, angle, side. Okay, so angle, angle, side, angle, angle, side. Alright, so that means that without having to do this third angle here, okay, and without having to show the other pairs of sides, we can conclude that triangle alpha, beta, gamma is congruent to triangle JKL. And so, angle, angle, side. So we're just talking about things that are kind of like moving in this order, so adjacent, okay? So you can see that these two are really similar. Angle, side, angle. We have an angle and then the side between them in an angle, and angle, angle, side. It's very similar, and that's just because of one more little property about triangles. So these are SSS, SAS, ASA, AAS. All you really need to know is that you're kind of moving along this to be like adjacent. So you start with an angle pair, then a side, and then an angle. So it has to follow that in order to truly show that they are congruent. Okay? So one thing to note is that there are actually a few that are not on this list of postulates. So these are our 4 postulates. So if we have this information, then these are the ones that we can count on. But what is notably missing is A. What about that? Angle, angle, angle. So the issue with this is if I have a triangle, let's say like so, if if I have another triangle with the same angles, could I conclude that the two triangles are congruent? Meaning the exact same lengths and exact same angles? And the answer is no. Because, for one, I can, if you want to rely more geometry here, you can draw lengths of sides that are parallel to each of these, but are a bit bigger. So like, say like so, like so. This triangle is going to have the same corresponding angles as the small one, the big one and the small one, as long as all the sides are parallel, or like corresponding sides are parallel. Okay, so this. So you can pick that up and move it over if you want to draw two triangles with the same angles, but these are not the same triangle because clearly this outer one is bigger and have longer lengths of sides than this inner one, but they do have same corresponding measures for angles, and that's because these are parallel. And so if you kind of extended this, we don't have to get into the geometry too much here, but if you extended this and we have two parallel lines with the traversal, then this angle is actually going to be the same measure as this one. It's that kind of idea. So if I extended this with this being the traversal, so it's actually going to be this way, this angle is going to be the same as this one, and same for all the other sides. Point being, if we have three corresponding pairs of angles being the same and congruent, but no information about the sides, then these triangles are actually what we call similar triangles. They have the same shape, but are not exactly the same. So it's like multiplying it. The ratios of the sides are constant, but it's kind of like taking that same shape and doubling it. So we know nothing about congruent. Well, they're not going to be congruent. Well, I guess theoretically they could. The ratio could be 1, but we cannot conclude that just because two triangles have the same measures for angles that they are congruent. Now, another one that's more inappropriate, so I'm going to write it as SSA, but you could read that backwards, is not. Also not a postulate for congruence, thankfully. That'd be kind of embarrassing. But SSA is side angle, and what that basically means is if we have two pairs, so remember this order matters because S is 1 but not SSA, and that's if we have two sides that are, let's say, congruent, so here, and then another side, let's say, is given here and here, but then the next thing would be an angle. Okay, so like some other angle, let's say they're congruent here. Can we conclude that they are going to be, the two triangles are going to be congruent? So the only way to kind of show this is kind of using a counter example, right? So if I somehow have an angle and then two sides that are that are the same, so let's start with the angle then. Let's say like this. So let's say this is the angle part, and then we move to a side, so this and this are the same. There is such thing as having two ways to make this side and this side congruent. It could be like something like that, perhaps, but it can also be like that, perhaps, because anything that I sweep here would be the same length. So then there's one that's kind of this way that makes it an acute angle, and then this way that makes this an obtuse angle. Maybe it would be further out, but I'm trying to kind of make a point that this length can kind of go inwards here, but it can also go outwards here. I guess that's one way to intuitively, show that that's inconclusive. So if we have one of the angles and we have a side and then another side, that this could be this triangle. So these two would be congruent, but we could also theoretically also have this case here, which these two triangles, the outer one, these two are obviously not congruent. So it's inconclusive, and it's kind of like, if you learned trigonometry, it's kind of like the ambiguous cases with, I believe it would be sine in this case. So it'd be kind of like an ambiguous case. So we don't have to prove that here, but basically making a point that SSA or ASS is not one, and neither is AAA. Okay, so the 4 would be SSS, SAS, ASA, AAS. So your SAS is okay, A-okay, okay? So SSS, SAS, ASA, AAS, but not AAA or SSA, okay? Alrighty, so take your time taking a look at this. Start getting used to this a little bit. If you have taken trigonometry, then it's actually quite interesting. Or if you've actually done more geometry, you can actually kind of show that these two are very similar, basically the same thing. These two kind of come together because of this third angle. And I think the rest would have to be proven with a little bit of trick, but anyways, I hope that this was a good little review, or maybe a little introduction, or if you're asleep by now, I'm wishing you sweet, sweet mathy dreams. If you're ready to continue on with the rest of your day, I'm wishing you a wonderfully blessed day, wonderfully blessed rest of your week. I'll see you around for more math very, very soon. Thanks for hanging out with me. Bye-bye.